So, on this most wonderful edition of NGR 315-A, we are going to be finishing our discussion of thin wall pressure vessels, followed by something called the return of Mohr's circle. Dun, dun, dun. So, a couple of notes before we get too far into it, though. Just a reminder that any rework or that you'd like to submit concerning the recent test is due, today by 5 p.m. And that's for half of the points that I missed. This means I'm probably not going to be given a whole lot of partial credit, but I'll give you a fair grade for whatever you submit. So there's that. We have 2 more classes left, if memory serves, following this one. So the next week we're going to talk about buckling on Monday. So it's another failure method that does not necessarily involve yielding as the initial method of failure. And then Wednesday is going to be for any review that you like to do. So if you have any questions, hook them up between now and Wednesday, right? Wednesday of next week. Send them to me early if you'd like me to prepare something else next Wednesday for you guys. Yeah. I said we'll have one more homework assignment that will be due next. That'll become available today. And I think that's it. If there are no questions, we will get rolling. All right. So yesterday, 2 days ago, Monday, we talked about pressure vessels. So it said that pressure vessels just a structure that holds a pressure difference between what's outside of it and what's inside of it. What were some of the key parts, some of the key assumptions about thin wall pressure vessels? And in our analysis about what were some of the assumptions we took?
The radius was more than 10 times the thickness of the wall.
Yep, that was our wall assumption. The ratio of the inner radius of the vessel to its wall thickness is greater than 10. That's our thin wall assumption. What other assumptions did we have here?
No stress concentrations.
Right. So like when we look at the analysis of a quote unquote real pressure vessel, we have like ports and all this other crap, and you see stress all over the place. We're all of that. We're assuming that there's no real change in geometry, that the length of the vessel, everything's axisymmetric, the pressure is uniform internally and externally. So all the stresses are evenly distributed across the length of the pressure vessel. And as a result, there also it doesn't just apply to things like this port here or like these other interruptions in the length of the vessel. It also applies to things like this, which you might think of being like an effect of having a sudden change in curvature, like there's a fillet here, a stress concentration. We're ignoring that. So we're assuming some uniformity and symmetry. There's the word in our stress distributions. Okay. We also said this is not an assumption anymore. This is our analysis. When we started the analysis on this, what kind of stresses did we have? Was it all normal stress? Was it all shear stress? Was some of both? What did we talk about yesterday? Do we have all normal stress, all shear stress, normal stresses and shear stress? What did we see when we started cutting sections?
Oh, the normal stress.
Right. It was called. We've only cut one section so far, but right now all we've seen is normal stress, and that's what we're going to continue to see. It's called due to our thin walls, assumption. Our assumption walls cannot sustain any bending, which is also a fairly good assumption. That's why people put so much work into level the ground underneath the tanks, make sure that they don't settle. Walls are thin, so the piece of sheet metal is really easy to bend. So the walls can't really be bending, and based on how we figure out shear stress distributions, it also means that they can't really sustain any shear stress. They can't support any shear stress. So we're going to ignore all that and say that there's only normal stress in the walls. So, being only normal stress, we've already derived a expression for longitudinal stresses. So if I go to the next slide, the next slide. So in this bottom picture here, I'm looking so that this guy is like looking down the middle of the pressure vessel, and we derived an expression for the stress kind of in that hoop of okay. So in that circle, due to the pressure vessel to pull apart like that. The background that you can actually see on. So that's here, and it's trying to pull apart like that. We the amount of stress that the internal pressure causes in the material due to stress in that direction. So today we're going to cut a section going the other way. So I'm going to hop over to my camera. We might say cam if you want to do like the kids these days. Kids with the Z, of course. So we have our pressure vessel. This is like a top view because it's axisymmetric. Side view is the same as the top view, right? And then if I look for like front, it's like that. So previously we had cut a section that looks like that. So let's cut a section that looks like you're looking at it from the front. Now we're going to look at it from say top view. We're going to kind of cut a section like that. Actually, we're going to take a chunk out of it just for kicking, just for kicks and giggles. So we're just going to look at say like that chunk there. Okay. So if I can draw this in 3D. So we are inside of the vessel, the stuff under pressure, right? Again, if you like Queen, this is a great chapter for you. You know that some pressure acting on it, right? It's pressurized. There's fluid actively pressing on it with some pressure. We call it P internal, or the internal pressure. Said that the tank has some radius. And we're just looking at some slice dx of the pressure vessel, four kicks and giggles. So does this? Oh yeah, and there's a wall thickness here. I forgot about the wall thickness. You can't forget about the wall thickness. Okay, so is that everybody diagram clear? And two, is it big enough to see? Sounds good. If no one says anything. Cool. All right, so the question is that if blue stuff's the fluid and this guy here are the walls. Question is, what's the stress in the walls, right? So how did we go about figuring it out last time? How did we figure out stress last time? What was kind of our modus operandi for doing that?
We used hooks, or we used the relationship F over A equals stress.
Okay. And why were we trying to find a force?
We summed the forces.
Right. Hey, we just did a summation of forces in the direction that we cared, the direction that we cared about. Made some substitutions from the definitions of stress and solve for what we wanted. So we're going to do the exact same thing. So we're going to do a summation of forces in, if I can put some directions on here. So this is kind of going, so this is a direction perpendicular to the wall or the fluid. We're going to do a summation of forces along that direction, all right? And we'll call that direction positive. All right. Let me fold this a little bit so we can keep it in view. Go. All right. I'm doing my summation of forces. What are my forces? I know that I have this pressure thing going on. I should write that I have some stress that's being communicated through these walls. So where are my forces coming from here?
Fluid in the wall.
Okay, cool. So how can I get forces from either of those? Pick your favorite one. Tell me how to get a force out of it. How do I get a force pressure? That's another way of thinking about it.
Well, one of them is going to be distributed.
Say again, please.
Well, the force from the fluid is a distributed force.
Okay, great. And what is the area that it is distributed over?
just the shaded region, right?
Okay.
Or actually,
No, you got it.
okay.
Because the fluid it only exists in that shaded region, right?
Yeah.
Yeah. So that's the only place that it can touch. So it's over that shaded region. What the pressure is. So what do I need in order to get the amount of force that corresponds to? Is it related to like area at all?
Did you say the force of the wall?
There is a force who's that's inserted on the wall. Yes. Question is, it's distributed too, right? Because it's called, if it's an internal force, it means that it's a stress. So how do we get a? So this is the same kind of question. How do we get a force from those from those? And also, if anyone which call is the which call are things too blurry for anyone else? I just saw that comment from Nick.
No, like I can see everything fine.
Okay. Yeah, I'm not sure what else I can do then, Nick. I'll try to write big.
Thank you.
But how do I get a force from a stress? How did we do it last time?
You find the area.
Yeah. And we said like a normal stress is equal to force over area, right? So if I know the area, I can force. So in this case, talking about the stress in the wall. What's the area associated with the wall in this particular free diagram?
You'd have to do the surface area of the section.
Okay.
So you do a cylinder.
Well, hang on a second. The section that we're looking at here, yeah, it's cut out of the cylinder. But what shape of this actual section where all the forces are acting on?
So you could just do a rectangle. That's like
You got it. So what's the area of just the walls?
P times delta X.
Awesome. Is that the area of just one of them or both?
Just one of them, so times 2.
Okay, so the area that we're looking at for the wall, the 2b delta x, t being the width, or t being the height, delta the width. There's 2 of them, so you multiply that by 2. We want to get an expression in terms of stress, so even though we don't know it, that's fine. We want to keep that in the equation. That we don't necessarily want to hang around is force. So I'm looking at my free diagram. How have my force arrows all going out of the wall, the same direction as my positive direction. So I can say sigma wall times 2t delta x is my one force. But that's not all my forces, right? What are my other forces? Do I have anything balancing this? Danilo was talking about it before. The fluid's pressing on itself too. Like there's fluid on which if I was sitting on this section and I was looking that way, like this is looking away from the section, I'd be staring at more like gas or air or whatever was being compressed inside of this tank, right? And that'd be pressing on me with some amount of pressure. So, how much force is exerted by the pressure that's pushing on the fluid in this section? Another way of thinking about it, you have some amount of pressure being exerted on this area, right? This blue area, there's some amount of pressure that's pushing on. How do I get a force from? How do I get force out of pressure? How are pressure and force related?
The pressure of the fluid times the area of that rectangle.
There we go. So we know that pressure is just a force over area. So if I know the area and I know the pressure, I can get the force that it's going to create. What's the area of that rectangle?
2r delta x.
Sweet. Oh my goodness, that's a terrible. 2r delta x. P is the pressure is the internal pressure. So it's something that we should know. So this means that force. So if I can add this into my summation of forces, that my forces looks kind of like this. I promise I'll put this up a little higher in a second. Something like that all equals 0. So same as last time. What I want to know is the stress in the wall, because I want to be able to tell if this thing's going to blow up or not. So I can solve for sigma wall. And get something like sigma wall equals P internal times R over T. Ignore all the stuff at the bottom. Cool beans? Any questions on that? Remember that R is your inner radius, the inner radius of the pressure vessel. and T is your wall thickness, and P is the internal pressure. Great. Or as the cool kids say, bada bing, bada bang. So cut two different sections through this thing. We've shown that, and those sections are, if I rotate them around at either axis of the pressure vessel, it give you the same thing. So we know that this. So if I know looking at a stress cube on the surface of the pressure vessel, if I cut out the skin, all that it's going to show is normal stress, no shear stress. So if I was to draw a Mohr circle here, it might look something like this. Actually, let me. Can I get rid of this piece of paper?
Yes.
Thank you. All right. So if I'm looking at my pressure, so if I'm looking at my pressure vessel again, and I look at a cube on it, I see stress going in the longitudinal direction, which yesterday or Monday we said was equal to P internal times R by 2T. I'll see a stress in the lateral direction, which seconds ago we said was P internal R over T. So those are our two sets of stresses on a stress cube. So I wanted to plot that on a circle. I wanted to draw Mohr's circle based on that. Well, one of the things I need to do in order to draw Mohr's circle, I need to know the center, I need to know the radius, right? The center of Mohr's circle is what? How do I get the center of this thing?
Stress.
Did you say average stress? I didn't quite hear you.
Yeah, is it? Well, is there the stress long ways and the one that we just did?
Yeah.
So would you have to subtract one from the other and then divide by 2?
No, Charles. Usually the average stress has usually been like sigma x plus sigma y over 2, right?
Yeah.
So I have two stresses in perpendicular directions and in the same planes. That's like a sigma x and a sigma y, right? If I call this my x direction, this my y direction, I have myself a sigma x and a sigma y, and the average stress is the average of those two. So it's just of them added. What you're thinking about, I think, is the equation for the radius, which we're also going to need. That's sigma x minus sigma y over 2 squared, plus the shear stress. Let me rewrite this a little bit larger, though. So these are just These are the same old equations that we've used for Mohr's circle, except now we've gotten ourselves into a situation where sigma y is not 0. So, we said that sigma x is our longitudinal stress, and sigma y is our lateral stress. And honestly, it wouldn't matter which one you picked in these, because like here it's added, it doesn't matter which direction I'm adding it. If it added sigma x to y or sigma y to sigma x, doesn't matter. I'm subtracting, but I end up squaring the results. It still does, so it still doesn't matter. So put these in the sigma long for sigma y. It really would not. This is how we draw Mohr's circle. We find the center of the circle, which is your stress, your average normal stress. You find the radius of the circle, which is this. We said that we have no shear stress here. So tau xy, what do I do with that?
Make it 0.
Woo! Right. Okay, so that's my radius then. So if I look back over and try to plot Mohr's circle then, here's my normal stress axis. Here's my shear stress axis. We'll say that that's my sigma average, which is going to be at what? So if I work that, it's going to be what? 2PR, so 3PR over 2T over 2. It's going to be 3/4 PR. PR over T. And then and then I know that same as when we did hold on, I want to say this. And if we look at radius is going to take us from sigma x on one side, or like sigma long lat on one side, and then sigma lat on the other side. Those might be switched. I'm just putting them there because I know that they go between them. Because I don't have any shear stress in how I solved it. I know that in Mohr's circle, I'm going to call it in my kind of original state of stress, the one that I've drawn here. I only have normal stress, so therefore in Mohr's circle, I expect the stresses computed to end up on my sigma axis, or in other words, where shear stress is 0. So the overall idea here, this is kind of what we've done for weeks. This should feel kind of familiar to you. Are there any questions up to here? Questions? Okay, so this gets fun then. So This is Mohr circle for that 2D stress element. But what you might be thinking is, wait a second, it's not a 2D thing, right? If I cut out, if I go in with a welding torch and I cut that stress out of the hull of the pressure vessel, it's going to be a 3D thing. It's going to be a pocket metal that has thickness, width, and length. It's 3D. It's called it has volume. It's not flat. So we need to think in 3D too. We need to be able to get stresses in 3D. So if I look here, I have sigma x, I got a sigma y. Might think I also need a z. So we never saw in any of our free body diagrams a sigma z. We didn't see a stress that was coming into or out of the page. We never saw a force that went into or out of the page. And if there's no force, there's no stress. So our sigma z must be 0. So if I kind of wrote all my stresses, if I identified what sigma x is, if I identified what sigma y is, and we've said there's no force perpendicular to them, so sigma z is 0. Y'all following me? Okay. So if sigma z is 0, I can draw another Mohr circle that goes between the, if this circle goes from the x direction to the y direction, I can also draw from the y direction to the direction. And z is 0, so I conveniently have two ends of the circle here, right? If I have both ends of the circle, then I have the circle diameter, right? The circle's diameter is just the distance from sigma lat in this case, sigma lat and sigma z is 0. So I can draw a circle there, and that's my YZ circle. This is my XY circle. That's my from Y to Z. I can also draw XZ circle. This is circles between Y and Z. Well, there's a circle from X to Z. And again, I have two ends of the circle from here to here. So I have the circle's diameter. So I already have all the information that I know and that I need to know in order to draw the circle, right? I know that the circle lies entirely. I know the diameter of the circle lies entirely on the sigma axis because all my stresses are on the sigma axis. So I have a diameter. I can get an average. I can draw the circle. Done. How are we doing with that?
How did you know that it's 0 for sigma z? Is it always going to be 0, or how's that work?
Did we find any forces in a z direction?
No.
Therefore, is there any stress?
Well, no, I get that,
right.
But like
right, and that's the trick. If there is force in the z direction, then there is stress in the z direction, and we can't say that it's 0. Am I going to give you a problem with that?
No. Problem, basically.
What? Say again, please. Sorry.
So that would be like outlining the problem, like force in the x, y, and then there's also force in the z. So you'd obviously get something, but like.
Correct.
Okay.
Correct. Yeah. And honestly, that lies outside the scope of this class. So I'm not going to give you a problem that has force or stress in the z direction. I just want you to get it used working with the fact that even though you don't have any stress in that Z direction, the maximum shear stress is actually highest in that direction. Like if I went by my usual Mohr circle, the one that I computed at first, my maximum shear stress would be like there, right? One radius of the circle from the center, right? But now my maximum shear stress here. It's much higher. So it's necessary that I not just consider 2D Mohr circle in order to predict failure, 3D Mohr circle. Even though I don't have any shear stress in my XY plane, and even though I don't have any stress in the Z direction, the maximum shear stress on my 3D stress cube is highest in an out of plane direction. So I need to consider it if I'm going to estimate when this thing's going to fail.
All right, that makes sense. Thanks, Brother Morris.
Okay, cool.
I think I hear you saying.
Okay, cool.
So what does... I'm just confused what the two circles represent. Like the two new ones.
So if I'm looking at 2D stress cube, right? 2D stress cube. And I have some sigma x, and I have some sigma y. Yeah? And if I want to be complete, I also have like shear stress here, right? Like that's 2D stress cube. Does that look familiar?
Yeah.
Okay. If you pop back over to the slide for a second, that's what a 3D stress cube looks like. You've just taken that 2D one, you've pulled it out of the page a bit, means you have to add in a sigma z, and you have shear stresses that are also perpendicular to one another. Okay. So if I looked at, say, this circle here on the right, this guy between A and B, that's my original 2D stress cube. Okay. But now I have two other faces. So this guy went between, say, like X and Y. Like my sigma x over here at A, my sigma y over here at B. Now I have sigma y over here at B, sigma z over here at C. So each circle is kind of turning the cube and looking at it from a different face. So one, I'm looking at kind of, I'm looking at it from, say, this direction. So I see sigma y going up, and I see x going this. Okay, I draw first circle. Then I turn the cube. I start looking at it from this direction. I see sigma y and sigma z. Okay, I draw this. Okay, I draw this circle. Look at it from another direction. My last direction, I see sigma x. I see sigma z. I draw this third circle. Does that make some sense?
Yeah. So when
Okay.
we're always drawing the circle, we'll always draw the x, y. Those are the two stresses that we can solve for by cutting sections.
Yep. And then what you call it, so you look, so you look at that first, then say, okay, great. Then look at your sigma z, say, okay, it's 0 or whatever. Okay, so I can draw between one of these stresses and that guy, or one end of my xy circle and sigma z, great. And then draw your last circle from the 2 points that you haven't connected yet, pretty much. That process makes sense?
Wait, how do you solve the CB circle again?
Yeah. So here, if you pop back over to the document camera. So from what we just did, I'm just labeling my axes. We know that we can get the AB circle. Oh, it's yours.
Yes.
So so we know that we can get sigma average. We can get a radius, and we can draw that circle no problem, right?
Yeah.
Great. And in this case, the thin wall pressure, this pressure vessel thing, we've said sigma x is sigma long, sigma y is sigma lat, and sigma z is 0. Great. And for reference, this is like your 2D Mohr circle. So this is the circle that you've always drawn. We've always done it that way. That's our 2D Mohr's circle. And because our free body diagrams did not have any shear stress in them, we know that one of these sides is sigma lat, one of these sides is sigma long, right?
Yeah.
Okay. Great. So if I look at my stress cube, which is truly a cube now, it's not just me saying that it's. If I looked at it from this direction, I see a sigma x and a sigma z. I'm going to pick this cube up and I'm going to turn it. When I turn it, say I just rotate it like that, so sigma y is facing up. Now I'm going to see sigma z and sigma x instead. Does that make sense?
Okay.
I just picked this up and I turned it 90 degrees. If I wanted to see sigma z on this one, it'd be like there, pointing straight up at me. And I just rotated that cube so that it's pointing up now, or it's pointing that way, and now sigma y is pointing straight up. Okay. So now if I just look at this like a 2D stress cube again, now I see sigma z and sigma x. So I'm going to draw a Mohr circle for those now. Okay. So going back here, I know that sigma z is 0. Sigma x is over here. There's no shear stress here. So I know that so I know that these two form a diameter of the circle. So I can just draw my circle between them. If I wanted to find the radius, it's just half the diameter, right?
Yeah.
So it's just sigma minus sigma z over 2. That's my radius there.
Okay.
Okay, so that's one. Now I can take this puppy again. I could keep rotating it this way, but I just go between this and this, right? So I'm going to rotate it that way. I'm going to drop. I'm going to drop the y where sigma x. So something like that.
Okay.
So now again, is now pointing straight up. So again, I look at this like a 2D thing. Okay, max and I have sig and I have sig and I have sigma. So I can find like an average and all that jazz. But I can also back over here and say, well, there's sigma y, there's sigma z. That forms a diameter, right? I can just draw a circle between those two because half the diameter is the radius. It also says that the circle is one radius away from either of the ends, right?
Mm-hmm.
Cool. So as long as I know 2 points on the circle, I can draw the rest. I can draw the rest of it. I can get a radius. As long as I have 2 points on the circle that are opposite one another. And by definition, all these points, all 3 of these points are all opposite each other on the same on their respective circles.
Okay, that makes sense.
All right. So we'll run through a example of this on Monday and go from there. Are there any other questions?
Nope, I think we're good.
All right.
Or at least I'm good.
All right.
Thanks, Brother Mohr.
Bye.
Have a good
All right,
one.
thank you.
Y'all too.